Alright, so this is your worksheet for balancing chemical equations. So when I was learning this in school, my chemistry teacher taught me the set of rules. She gave us a list of rules to follow while we solved the chemical reaction. And then I saw on your worksheet that it also said to identify whether it was a combination reaction, which is known as synthesis, decomposition, combustion, double or single replacement, and how you know. So I'll go through that with you. So these were the list of rules that she gave us when I was in school learning it. So whenever you're given the equation, the first thing we have to do is to check to see if it is balanced. So if we look at your first problem, you have some odd number of aluminum phosphate in an aqueous solution plus some number of iron 2 chloride. I say iron 2 because we know that chlorine has a -1 charge and that this 2 came from dragging down. So essentially this is a review of that. So we know that the Fe had a +2 charge, that the chlorine had a -1 charge. That charge basically came down, and that's why we have this. But that's not directly what we're here for. Okay, and then it goes to aluminum chloride solid and also produces some amount of iron 2 phosphate. So we gotta first check to see if it's balanced. So here we have one aluminum, okay, so the aluminums look balanced, but we can't just end there. Here we have one phosphate group, because that's a whole polyatomic ion, but over here we have 2, so it's not balanced. So our equation's not balanced, so that leads me to rule number 2. Rule number 2 is to balance your polyatomic ions as a whole group. Okay? So if we balance them as a group, if we have 2 here and 1 here, what we can try first is to try to put a 2 here and see if that works. So if that means we have 2 phosphates, we can check that off. Okay? But now we have 2 aluminum. And down here we only have 1. So that's not balanced. So now we have to balance out the aluminum. So we'll try it with a 2. So now we have 2 phosphates, 2 aluminums on each side. So that checks out. But now our chlorines are unbalanced. So we originally had 3 here, but now this 2 will use the distributed property and carry out. So 2 times 3 would be 6. So on the product side, we have a total of 6 chlorines. But on the reactant side, we only have 2. So we have to get total of 6 on the reactant side. And we know that if 2 times 3 equals 6, then 3 times 2 also equals 6. So now our chlorines are balanced out. So now everything is balanced out except for our iron. So now we have to see if our Fe balances out. Okay, so 3, we have 3 irons because there's an imaginary subscript of a 1 there. But we just don't write it like that. So 3 irons on the reactant side, and then do we have 3 reactants on 3 irons on the product side? Yes, we got 3. So now that everything balances out, all of our independent atoms balance out, our equation is balanced. So it would be 2 aluminum phosphates excuse me, plus 3 iron 2 chlorides plus 2 aluminum produces 2 aluminum chlorides plus 1 iron 2 phosphate. And that's essentially how we'll do each one of these problems, step by step. The type of reaction that this is what we would refer to as a double replacement. So double replacement. commonly referred to as Dr. Okay, we know that it's double replacement because if we look at the phosphate and the chlorine of the reactant side, they swapped. They swapped places. The aluminum and iron stayed the same. So your reasoning could be that the metals had different partners on the reactant / product sides. And just like that, we have completed our first chemical reaction.
She's the one that sent you the message going now.
Yes. So, this is now question number 2, or problem number 2, reaction number 2. Okay? So, we're going to use those same rules, okay, that we were given, but we're going to go through this reaction. So, we have C5H12, which I believe is pentane. It's a simple alkane, pentane, in the presence of oxygen gas, produces, this symbol means produces, liquid water and carbon dioxide gas. Okay? So, we need to see if it's balanced. Clearly, it's not balanced because we have 5 carbons here and only 1 carbon there. So, clearly, it's not balanced. We now can see, do we have any polyatomic ions as a group? Well, if we look at this, I don't see any polyatomic ions, which your chemistry teacher, I don't know directly if your chemistry teacher did do it or not, but our chemistry teacher had us memorize those polyatomic ions, so that might be something that they have you do. It's up to your teacher, whatever they do. Okay, so we can't use rule 2 because we don't have any polyatomics. So now let's look at rule 3. Okay, so it says odd and even with a 2. Well, we have a mixture of odds and evens. So we might have to do that. So typically what we do there is we put a 2 at the beginning of this. Now, this doesn't always work. Sometimes you get lucky and it works, but not all the time does it work. So, again, we use the distributive property. 2 times 5 is 10 carbons. So, 10 carbons. Okay? So, now we need 10 carbons over here. So, then that means we got 10. Now, our carbons balance out. Okay? Again, this doesn't always work, but we're going to see if it works. Okay, but now, we always balance hydrogens last. We never do hydrogen next. We always balance hydrogen last. It's a thing. It's just a general chemical rule. Okay, so now we have so 20 oxygens here, plus 1. So that's not really a thing that we like. So in this case, we're going to have to break that chemistry rule and balance out the hydrogens before we can balance the oxygens. That's not always the case, though. So if we look up here, we have 2 times 12 hydrogens. So 2 times 12, 24 hydrogens. So that means if there's 2 hydrogens here, and we know that 2 times 12 is 24, then that means 12 times 2 would be 24. So then our hydrogens balance out. But now we have to balance out the oxygens and make sure that they're balanced. So then we have 12 times 1, so 12, plus we have 10 here, times 2, that's 20. So 12 plus, you'll do 12 plus 20. That gives you 32 oxygens on your product side. Okay? So that means you need 32 on your reactant side. So then if we have 2 oxygens already, we just have to divide 32 by 2. Well, 32 divided by 2 is 16. 16 times 2 is 32. Okay? Now our equation is balanced. However, this is not our final answer. All of these numbers, all these big coefficients, are even and divisible by the number 2. So we can divide each of these coefficients by 2 to get our final answer. So this 2 ends up becoming a 1. This 16 becomes an 8. This 12 becomes a 6. And this 10 becomes a 5. Okay? Once it hits an odd number, we can no longer reduce it or simplify the equation. This is the most simplest form. So this is our ratio. This would be your final answer. Now, anytime you see a reaction like this, typically on a written response you'd see burned in the presence of oxygen. So anytime you have something that starts with a C with some number, H some number, and it burns in oxygen, the type of reaction that it is going to be is called a combustion reaction. We label this as the letter C, not to be confused with carbon. That's why we draw a circle around it. Okay, so it's a combustion reaction. Your response to that would be, it is in the presence I can't spell today, in the presence, there you go, presence of O2 gas, and produces H2O, liquid, and CO2 gas. So that's what you'd write on that one. I'm hoping that this is somewhat making sense. Okay, so moving on to your third problem. Okay, you have iron metal in the presence of liquid solution, so water solution, producing Fe3O4 solid, which I can't remember what that directly is off the top of my head. Okay, and then hydrogen gas. So essentially we do the same thing here. We look at the irons. Okay, we have 1 iron here, 3 irons here. Okay, so we could balance that, say with a 3, because we know that it's not balanced the first. Okay, so if we do that, irons check out, right? So check, check. So we'll just say there's a 1 there. But now it says that there's 4 oxygens here, but there's only 1 oxygen here. So we would need 4 there. So that would give us 4 oxygens. So now that checks out. But now we have 4 times 2 for hydrogens, or 8. Okay, and then now we need to go over here. We have 2 hydrogens here, but if we have 8 here, we have to multiply this. So if 4 times 2 equaled 8, then 4 times 2 here equals 8. So now our hydrogens match out. And we are simplified because we have an odd number. So 3 to 4 to 1 to 4. So 3 iron solid molecules to 4 H2O molecules produces 1 Fe3O4 molecule to 4 H2 molecules. Okay, so as it comes to this type of reaction, we only see one thing different, right? So that means this is what we would call single replacement, or SR. Okay, so SR. So we only know single replacement, and our reasoning is the iron, you could say the iron was alone, but was bonded with oxygen in the products. I'm hoping that this is making sense. I'm sorry, I'm trying to balance my camera on one hand and write this. Okay, and then this is basically just the same thing over and over again. So just following these rules. Most of the time you typically end up stopping at 3. Very rarely do you ever have to get to 5. There are some times that you do have to do that, but it's very, very rare. You can also use the jumbo subscript sometimes if you have really big combustion reactions or other types of reactions. But 4 and 5 you don't use very often. 4 more so than 5, but not very often. Okay, so number 4. You have UO2 solid plus hydrogen fluoride producing UF4 solid in water. So first, is it balanced? Well, let's see. We have 1U, 1U. 2 oxygen. 1 oxygen, so nope, we're not balanced. And we can also see that the F's aren't balanced, or the H's. So the only thing balanced is the U's, but not anything else. So, do we have any polyatomic ions? Not really. So, we have to ignore rule 2. So now we have to try odd even with a 2. Well, we can't really do this because the U's are already balanced. So, this is where we get into 4. So, F has 4. So, jumbo subscript. So if F has 4 on the product side, now we have to figure out what times 1 is equal to 4. Well, that's 4. So we have 4. So now our F's balance out. Okay? And if our F's balance out, that means now we have to balance out the H's. So 4 times 1 H is 4. We have 2 H's here. What times 2 equals 4? 2. So now we have 2. Okay, so 2 H2O. 4 there. Okay, so now the hydrogens balance out. Now we have 2 oxygens. 2 times 1. 2 oxygens. So those balance out. And our U's balanced out. So both of these will just be a 1. And we are simplified. Okay, so 1 UO2 goes to 4 HF, producing 1 UF4 plus 2 H2O. Now again, like the other one, the U started with oxygen, but went to F, went to fluoride. Okay, and then the hydrogen started with fluorine, but went to oxygen. So this is double replacement, or DR. Okay, and then explain how you saw that. Using what I've taught you thus far. So explain how you know it's a double replacement reaction. Okay? We're going to go to the next one. Okay, so number 5. This is where that jumbo subscript is going to really come in handy. Really going to come in handy. Let's see. Now we have an octane. Octane gas, in the presence of oxygen, produces water, carbon dioxide. Oh, this looks familiar. That it do. Okay, so we have 8 carbons here, 1 carbon here. Jumbo subscript, because we don't have any polyatomics. It's not balanced, obviously, and we can't just simply do this with the 2. So now jumbo subscript. Okay, so we'll put an 8 down here. Carbons balance out. Okay, but now we have 16 oxygen here, right? Plus 1 there, so that's 17. But what we also have is 2 hydrogen here, 18 hydrogen here. Well, if our carbons balance out, let's make this a 1 real quick. So if that just stays at 1, that means there's 18 hydrogens on the reactant side. But we need 18 on the product side. So what times 18? What times 2 equals 18? 9. So 9 times 2. Okay, 9 times 2 is 18. And then you have 9 oxygen here, plus 16. That gives you 16 plus 9, 25 oxygen. And then you have 2 oxygen here. So then this is where it gets a little tricky. Because sometimes the jumbo structure doesn't always work. But this is one instance where I think this is where it's going to have to work. So since there's 25 oxygen, it's going to essentially end up becoming 25 halves oxygen. But I'm going to see something real quick. So if I do 2 there, that's 18. We might have to do this another way to get it to come out even. So if we do it that way, it'd be 18. If we try to do it with a 2, trying to multiply the 18 by the 2, that'd be 20, so 36 total. So if this became a 2, I'm just free writing at the moment. So if we did a 2, that'd be 2, that'd be 36. And then you'd have 36 here, 36 divided by 2 would be 15, 18. So then that would be 18, 2, 18. Okay. So then that would give you 16 here. And then if you multiply, let's see, that'd be 16 times 2 here, so 16 times 2 is 20, 32 plus 18 would be 40, 50. So this would be just simply multiplied by 2, which that would cancel out. So then that would be 50. Which, I mean, looks a lot nicer. Because we don't really like seeing halves. So, what I would do on this one would be to write both of those. I'd write the overall one here. I'd write the 2. So I'd write the 2 there, 18 here, the 50 here, and the 16 here. Okay? But then, in your explanation, you could say simplified would be 1. So, like you could say, simplified is, well, simplified ratio is 1 to 25 over 2 to 9 to 8. But I would go ahead and write in that this is 2, that this is 15, that this is 18, and that that's 16. And this is a combustion. Or C. And again, burned in O2 gas and produces H2O and CO2. Sorry, I keep moving my phone. Again, I'm not entirely sure what your specific teacher would prefer. So I would go ahead and write the simplified ratio there. But in this, I would write the 2, 50, 18, 16, and leave it at that. And then be like, okay, I could have simplified it to this, but I felt safer with this with a whole number. And see what she has to say. Okay, number 6. Boron trifluoride and water react to produce hydrogen fluoride or hydrofluoric acid. Debating on what's going on. And hyperbromate or hydrogen bromate. Yeah, this is hydrogen bromate because bromate is a polyatomic ion. So hydrogen bromate. Okay. So we got to check to see if it is balanced. So boron here, one boron there, that's good. Three fluorides, only one, so not balanced. We have polyatomics, yep, the BO3, but there's no BO3 over here. So we'll ignore rule 2 for right now. Odd even, we don't really need to do odd even right now. So we have 3 fluorines here. We need 3 over here. So 3. So fluorine is now balanced, right? But now we have 3 hydrogen here, plus another 3 hydrogen here. So that's a total of 6 hydrogen there. So if we have 6 hydrogen here, we need 6 hydrogen here. So we need 2 times something. Well, 3. 2 times 3 hydrogen. So 6 hydrogen. 1, 2, 3, 4, 5, 6. Check. Okay. Put a 1 there. Okay, so 3 times 1. Remember, because 1 subscript. 3 times 1, 3. Got 3 over here. Oxygens check out. And now we have one boron to another boron. Oh, that's not bromate. I called that the wrong thing. Ignore me. That's boron. Okay. I remember calling it boron trifluoride up here, but ignore my name for that. It's been a fat minute since I've done this. Okay, so that we have 1 and 1. So we can write a 1 there. So we have a 1 to 3 to 3 to 1 ratio. Now as for the type of reaction this is, boron started with something here, but ended up with something different over here. Hydrogen started off with this here, ended up with this. So this is another example of a double replacement reaction. Okay? Explain how you know. I'm hoping the more and more that we are going through this, that this is understandable. Okay? I might be moving slightly fast and writing these, and I apologize, so you might have to pause and whatnot with the video. Okay, so number 7. Magnesium oxide and iron react to produce iron 3 oxide and magnesium. I say iron 3 oxide because of this 3 here. Okay, so we have 2 irons here, 1 iron there, so it's not balanced. 1 magnesium here, 1 magnesium there, 3 oxygens to 1. So we can't do all that. So we need to balance out the irons. Okay, so if there's 2 here, we need 2 over here. Okay, so now the irons check out. Okay, so we're going to assume that this is a 1 right now. So if there's 3 oxygens here, we need 3 over here. So that means that this has to be a 3. So now we got 3 oxygen. So now those balance out. 3 magnesium here. 3 magnesium there. And now we're balanced. Everything's balanced. So 3 MgO plus 2 Fe will produce 1 Fe2O3 plus 3 Mg. Okay. This is a single replacement. Okay. Because magnesium and iron basically just swapped places. Okay, so explain the single replacement. Okay. Oh, this looks vaguely familiar. The more you do this, the more familiar it gets. Okay. So this might be one of those other things where we might have to jumbo subscript it again. Or greatest common factor, in this case. Okay, so we have 13 carbon, 1 carbon, 26 hydrogen, 2 hydrogen. Okay, so already that's making me a little nervous with the simplified version of this. 2 oxygen, 3 oxygen. So what I'm going to do is I'm going to do greatest common factor, put a 2 here, okay, and the 26 here. Because then you know that your hydrogens are balanced out. That gives you 52 hydrogens apiece. Because 26 times 2 is 52. Okay? So now that gives you 2 times 13 carbon. 2 times 13 is 26. So that means we need 26 carbon here. So 26 carbons now balanced out. Okay? Now we have the oxygens. So 26 times 2, 52, plus 26 times 1, so 52 plus 26, 78, right? Because 20 plus 52 is 72, plus another 6, 78. So if we have 78 oxygens on the product side, now we need 78 on the reactant side. So what goes into 78 twice? Well, you can do a simple, quick little math here. 78 divided by 2. You got 3 there. 6 minus equals 1. Okay. Bring that down. Got 18. Okay. So then, how many times does 2 go into 18? Well, 9. 9 times 2, 18. Minus, you got 0. Alright? So 39 times. Which is beautiful, because that's an odd number. Which means this is our most simplified version of this equation, this reaction. So your ratio is 2 to 39 to 26 to 26. These can get very complicated. I'm going to let you name the reaction. Okay? It's very familiar. Okay, I'm going to give you a hint. That's its symbol. What type of reaction is that? Okay? And then explain how you know. Ah, now this is a different one. Okay, so we have ammonium nitrate, 2 polyatomic ions together into one compound, one molecule. Okay? And it produces, it's not reacting with anything, so, that's a hint. It's not reacting with anything. It's producing dinitrogen monoxide gas and water vapor. I say water vapor because the water is in a gaseous state. So water vapor. Okay? So we have 2 nitrogens here. 2 nitrogens. Okay? We have 3 oxygens. And then we have 2 oxygens. So our oxygens aren't balanced. And neither are our hydrogens. Okay? We have 4 hydrogens. 2 hydrogens. There's a simple fits here. Okay? If we look at the hydrogens, because the nitrogens are balanced, okay, so balance the nitrogens. So if we look at the hydrogens, we have 4 here, but 2 here. Let's try putting a 2 here. Okay, so 2 times 2, 4, got 4. Okay, that balances out. Okay, so then 2 times 1, okay, that's 2, plus 1, 3. Do we got 3 over here? Yes, we do. So 1 and 1. So our ratio here is 1 ammonium nitrate produces 1 dinitrogen monoxide gas and 2 water vapor molecules. Now this is a reaction that we have not gone over in this problem set from your worksheet. This is what we call a decomposition. So a reverse synthesis reaction. Okay? So a decomposition. We label it just as D. Okay? We explain this by saying there is only one reactant. There's only one reactant on the reactant side of the equation. Okay? So there is only one reactant on the reactant side of the equation. These are slightly confusing at first, but you'll start to notice a pattern as we have with the other ones. Hopefully you're picking up on the pattern. I'm doing my best to explain it the best I can. Okay. Problem 10. Krypton difluoride and water react to produce krypton solid, which krypton is not typically a solid, so this takes a lot of sublimation to occur. Okay, I don't know if you and your teacher if your teacher has discussed the phase diagram, how it goes from when it's called liquid to gas, evaporation, gas to liquid condensation, the phase diagram, each state going to each one, what it's called. So when you go from a gaseous form of a thing to a solid, because krypton is typically not a solid, it's typically a gas, it's called sublimation. Okay, plus oxygen gas and hydrogen fluoride. Okay? Now the hydrogen is reacting and producing a different compound, but the other two are staying the same. That's a key hint for this reaction. Okay? Key hint here. But we need to balance. We have 1, 1. But there's 2 fluorine, 1 fluorine. Not gonna work. So let's try to balance it out with a 2. Okay? We have no polyatomics here. So 2. So now our fluorine's balanced. Okay? Our krypton balanced. Okay? So now we have 2 hydrogen here on the product side. Oh, well that's just wonderful. We have 2 hydrogen on that side, right? But we only have 1 oxygen there, and we have 2 here. So that doesn't work for us. So this 2 doesn't work. So we can't do that. So if there's 2 oxygen here, if we leave this at a 1, to say that that's a 1, okay? Then that means we have to put a 2 here. Okay? So now the oxygen's balanced. But now we have 2 times 2 hydrogen. 4 hydrogen. 4 hydrogen. So now the hydrogen's balanced out, right? But now we have 4 fluorine here and 2 here. So simply, that can be balanced with a 2. So now we have 4 fluorines. So now the fluorines check out. So do that. Now we have 2 here, 1 here. Balance it out with a 2. So 2, 2. So those balance out. Okay. So now our equation is now balanced. This one is a little tricky on trying to tell what the type of reaction is, but the oxygen came out by itself. Krypton by itself. The hydrogen and the fluorine, however, combined. So if only one thing combined, this makes it a single replacement reaction. Okay? So explain the single replacement. If you need to pause the video and go back through my explanation that I gave you, then that is okay. I'm gonna give you a second. Okay. Number 11. H2NCl aqueous plus a polyatomic ammonia, okay, reacts to produce ammonium polyatomic chloride and dinitrogen tetrahydride. Okay, I don't remember what that's specifically called. I know it, but I don't remember it. So I'm just going to call it H2NCl. Okay, so we have 2 here plus the 3, so 5, 4, plus 4, 8. So this isn't balanced at all. And then 3 nitrogen here, 2 nitrogen there. I don't know if I like all that. So we're going to have to figure out some confuddling here. So, I think what I want to try first is putting a 2 here and see how that works. We'll try it. So now we have 2. Oh no, odd and even with the 2. Don't do that. Remove that 2. Let's put the 2 here. Okay, because then we get a nice even number of hydrogen. And I love a nice even number of hydrogen. Okay, so that means 2 nitrogen here plus here. That's 3 nitrogen. And then 1, 2, 3 nitrogen. So the nitrogens balance out. Excuse me. Okay. And now we have 2 times 3, 6, plus the 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen's balanced out. It's beautiful. And now our chlorine. 1, 1. Chlorine's balanced out. It's beautiful. So 1, 1, 1. So 1 H2NCl plus 2 ammonia produces 1 ammonium chloride and 1 dinitrogen tetrahydride. Okay? Balanced. Now the chloride ended up swapping, and the nitrogen didn't really swap, but it added on 2 different things. So we started out with 2, ended up with 2 different ones. Double replacement. Okay, explain how we determined that. Alright, number 12. You got sodium carbonate plus carbon solid diamond plus nitrogen gas react together to produce sodium cyanide, polyatomic, and carbon monoxide. Okay? We got 2 sodium here, 1 sodium here. 2 carbon, 1 carbon, 1 nitrogen. Oh, wait, hold up. 2 carbon, 2 carbon. 1 nitrogen, 2 nitrogen, 1 oxygen, 3 oxygen. I don't really like dealing with odd numbers of oxygen. So what we gonna do is we gonna try a 2 here first. Because I just like an even number. So, that gives us 4 sodium. And we know that we have 1. So let's do 4 sodium down here. So the sodiums check out. Okay. Then we have 4 carbon here. 5 carbon. Okay. 1, that's 2, 3 carbon. See? But we have oxygen here. So let's try to balance that oxygen here. So we have 2 times 3 oxygen, right? 2 times 3, 6 oxygen. So we need 6 oxygen there. So now our oxygens are balanced. Now we have to get to our carbon. Okay? So we have 2 carbons here, because we're trying to find this number. But we have 4 plus 6, so 10 total carbon. So we already have 2, right? But we need a total of 10. 8 carbon. Okay? And then we have 4 nitrogen and only 2 nitrogen. So 2 nitrogen. Okay? So now our nitrogens, everything balances out, and it's a beautiful little thing. Okay? However, 2, 8, 2, 4, 6. This is correct, but there is a better answer. This could be simplified. So the 2 becomes a 1. 8 becomes a 4 because we're dividing everything by 2. Becomes a 1, a 2, and a 3. Okay? So that is our simplest form of this equation. 1 sodium carbonate plus 4 carbon plus 1 nitrogen gas goes to 2 sodium cyanide and 3 carbon monoxides. Now, this one is also a little tricky because the sodium changed, but some of the others changed too. So carbon here was single, nitrogen here was single, but there's carbon here twice, and only oxygen in 1. So, we technically produced 2 different compounds, but I believe that this is only I want to say single replacement, but I also think it's double replacement. So single replacement or double replacement. We are about to see. Let me see. Okay. So, after doing a little bit of searching, I'm going to bring back 10. Okay, so I told you that this was single replacement. It's technically still single replacement, but there's something else going on. It's a single replacement, but in the form of what we call a redox reaction. Okay? Basically, it's where one of the substances is being oxidized and the other one reduced. Okay? Oxidation reduction. Okay? But single replacement for the moment. Okay? Now back to 12. I originally thought single replacement and double replacement, debating with all this. However, after some consideration and some research, it is actually neither one of these. It is a combination reaction, or what we refer to as synthesis. Okay, which we refer to as the letter S, because it's a bunch of reactants combining to form products. Okay, so there's your explanation. A bunch of reactants to form compounds. So 2 or more reactants to produce compounds. Alright. Almost through all this. Whoop whoop. Alright. So, 13. Okay. You got ammonium dichromate, 2 polyatomic ions. Ammonium dichromate. Uh-oh. We've seen this before. 1 reactant producing nitrogen gas, chromates, solid, and water vapor. So, we obviously know that it's not balanced. 2 nitrogens, 8 hydrogens, 2 hydrogens, okay? 2 CRs, 4 oxygen, 7 oxygen. Obviously not balanced. But we have polyatomic ions, right? So, try to balance polyatomic ions as a group. Well, that's kind of hard in this specific type of reaction, considering that that specific type of polyatomic broke up. So we can't really do that. So we gotta now go the odd even with the 2. Kinda sucks. Okay, so we had 4 oxygen here, but we had 7 here. I don't really like odd numbers of things, remember. Okay, so 2, that gives you 14 oxygen. Okay, so we need 14 oxygen. Okay, so that gives us already 2 nitrogen here, plus another 2, 4 nitrogen. So we need 2 nitrogen there to balance that out. So our nitrogens are now balanced. Okay? So we already had 8 hydrogen here. Okay? From this. But now we have to multiply that by 2. So 16 total hydrogen. Which means we have to go 8 here. 8 times 2, 16. 4 times 2 times 2. 16. Hydrogens check out. Okay? This gives us 8 oxygen here. Plus 3. That's 11 oxygen. Not the 14 we want. It's disgusting. But, excuse me. 2 times 2 chromium, 4 chromium. Now we have 4 chromium. Okay? So 2 times 3, 6. So we got 6 plus the 8. 6 plus 8, 14. 2 times 7, 14. So now our oxygens balance out. It's a beautiful thing. It's wonderful. It's glorious. But is this our final answer? No. 2, 2, 2, 8. All even, they can be simplified. 1, 1, 1, 4. And it should get you the same thing. We've seen this before. Decomposition. How do you know? Okay. Give you a second copy. Kind of look. Last two problems. Look at that. Okay. ZN3 SB2 solid plus water. That's zinc. I think that's tin, but I can't remember the name of the compound. React together to produce zinc oxide and I think that's tin. I really want to say that's tin. Tin trihydride. Oh, tin 3. Yeah, tin 3 hydride. Okay, so we have 3 zinc here, 1 zinc here. 2 tin here. I only want 2 hydrogen here, but 2 5 here. 2 oxygen, 1 oxygen. Don't like it. Don't like it at all. Okay. Now, we don't have any. We have polyatomics here, right? Hydroxide. So this could be written out as H and an OH. Okay. Balanced polyatomic. 1 hydroxide. 2 hydroxide. Okay, so 2 hydroxide. This gives us 2 oxygen here. 4 hydrogen. We have 2 here, 5 there. So even though that's what we wanted to do, can't do that because it's not going to work out. So what we have to do now is balance these out. We have 3 here, but 2 here. So we got to put a 3 here, a 2 here, because that'll take care of the zinc and the tin, right? But now it leaves us stranded with the oxygen and hydrogen, right? We already have 2 here for the hydrogen times the 2, right? So we have 2 plus the 6. Yeah, 2. That's 6 hydrogen here. Plus 2. That's 8 times 3. That's... Ooh, hold up. I don't like that. So 3 here plus this. This is 2 times 1, 2 times 3, 6. Yeah. 2 times 1, so 2 oxygen times the 3, 6 oxygen. Okay, and then you got 2 here times the 3 is 6, plus another 6 here, because 2 times 3. So 6 hydrogen over here, plus another 6, that's 12. So 6 times 2, 12, and then we have the 2 oxygen times the 3, 6. So all of this balances out now. And we cannot simplify it because we have a 3 and a 1. So that is our finish. And this is what I would call double replacement. Explain. Okay. Alright, final problem. You have iodine bromide. Okay. Iodine. No, monoiodide, monobromine. Solid. I don't remember the name, but that's just the basic name because it's two nonmetals. Plus ammonia react to produce nitrogen triiodide. Okay. And ammonium bromide. We have polyatomics, but we can't balance them as a group because they're two completely separate. We have 3 iodines here, 1 here. We have 1 bromine here, 1 there, 1 nitrogen, 3 hydrogen, 4 hydrogen. So, I don't like all that. We're going to have to figure that out. Okay? So we have 3 iodine here. Let's try 3 up here. Just see where it gets us. Because then our iodines balance out. Alright. That gives us 3 bromine. So if we have 3 bromine, we gotta do 3 bromine over here. Okay? That balances bromine. Okay? But if we have a 3 here, that gives us 3 nitrogen here. And a 4th here. So 4 total nitrogens and 12 hydrogen. 3 times 4. So if we have 4 nitrogens, to 4, because that'll balance out the nitrogen. Does that balance out the hydrogen? 3 times 4, 12. 4 times 3, 12. Yep, hydrogen's balanced. 1 there. So your ratio is 3 to 4 to 1 to 3. This is another can't really say double replacement. Because double replacement is more of a reaction. So these are helpful tips that my teacher taught me. They're also on Google if you need to know. It says a decomposition reaction is a reaction in which a single compound breaks into 2 or more, simpler. Combination is 2 or more substances combining to form one single compound. A single replacement is one element replaces another in a compound. A double replacement is which a positive and negative ion of 2 ionic compounds exchange places to form 2 new compounds, etc., etc. So, this is more of an ion, almost. So, because this is just gonna... Yeah, so this is more of ion, so I feel it's not really double replacement. But I feel like it's more of a redox. Let me search real quick. Okay, so I did some searching, and my initial thought, if I said double replacement, was correct. It is a double replacement reaction, so double replacement. Explain. How you know? So that is it for those 15 problems. I hope that this has been helpful for you, and I wish you the best of luck.